Bismillah. Assalamualaikum warahmatullahi wabarakatuh. Respect the viewers of the IGN Talk Series weekend and all IGN boarding school, vocational, high school, college. Praise be Allah Subhanahu wa Taala who has given us health and we are still meeting at this evening webinar. Salat and greetings to our Prophet Muhammad Sallallahu Alaihi Wasallam has give us guide to follow the path of Allah Subhanahu wa Taala. So at this weekend webinar, held every Saturday and Sunday morning. Sorry, held Saturday and Sunday morning at 8 for sharing network material, RPL, and NDMM. To share knowledge that has been this webinar is held for free by IDN every Saturday and Sunday. I did introduce myself to audience. I'm Aniswati, a student from IGN and 11th grade as the host of this evening event. And Alhamdulillah, and also our speaker, our presenter Muhammad Hafiz, we is gonna bring basic material IP physics, IPv4, IP physics, and routing IP physics. We leave the time and place to our presenter.
Uh, Assalamualaikum warahmatullahi wabarakatuh. In this occasion, I would like to start with Bismillahirrahmanirrahim. Bismillah. And in this webinar, I would like to talk mainly about IP physics. But before getting to the material, what is actually networking? Like, I will start from the very, very basics. So I'll talk what's a computer network, then what's an IP address, what's IPv4, then IP physics, then routing, and then how to route IP6. So these are the topics that I'm going to talk about, which I just surmised before. Then firstly, what's a computer network? If you take a look at the definition from Wikipedia, it says that a computer network is a set of computers sharing resources located on or provided by network nodes. But what does it actually mean? Like in Wikipedia, Wikipedia is really impeccable, like accurately impeccable, but it's not that useful for common folks like me. So in here, I'm going to just split it up word by word definition, and let's find out what a computer network means. So after like what's a computer network? Firstly, it's a set of computers. So a set of computers basically just like one or more computers. So it can be like 3, 6, or 9, like a set of them. Then after a set of computers, each computer are sharing resources. By sharing resources, what I mean is, for example, if in a topology, on the top and a topology is like when each device but basically it's like the mapping of where the device is located and who is connected to who. Like here we have 3 devices, so there's a server, a file server, then there's a printer, and then there's a workstation, there's a PC. Then the PC is connected to both of them. So what does actually sharing resources mean? So imagine if there's a file you want to download, and it's not located on your PC. It's located in the file server. And imagine if that file is like a movie, for example, Squid Game. So usually type in your browser, you type download, like you type like Squid Game download, and then you search for the web, and then that usually goes to a server, and then the server that contains that file receives that message. It accepts it, it reads it, and then it prepares the file, and then it sends it back to your PC. And then the PC receives it, and then you can, and it's stored locally, and you can watch the movie and and enjoy. That's an example of sharing resources. So basically, a resource can be data, or even like uh, other resources like from the hardware, like memory. So memory, compute power, uh, and anything else, including storage, like the example. Another example is if you want to print something, you need a printer, obviously. You just can't print with your computer. So you need an external device, like obviously a printer. So you prepare a file. To print, you need to prepare a file, and then you send it to the printer. The printer receives the file, and then it reads it, processes it, and then it begins to print the file to actual paper. So by this example, it illustrates uh, each how it shares resources. So how each set of computers shares resources. And oh, I also forgot to mention that a server and a printer are classified as computers because a computer is basically like anything with like CPU, RAM, storage, and a server obviously has like all of those, and then a printer too, but at least it's not that much that it can be called. It can be used as a like a PC, but it's like suitable for printer. And furthermore, uh, what like located on or provided by network nodes. So what's a network node? In this Wikipedia definition, network node is either it's either a redistribution point or communication endpoint. So it's more like a network node. It's like a set of PCs, like each PC, they're connected to like a central device. They're connected to that device, and then it basically like redistributes like the network. So to give an example, imagine there's four PCs, but how are they going to communicate with each other? So you can just like connect all the cables to all of them. It's going to be well, it could work back in the old days, but if the network grows like more than four PCs, like for example 8 and 12 and so on, it's going to be a little bit complicated. So how do we solve this problem? Well, with an example of a network node is router. And you could also use a switch, but in this an example, I'm going to use a router. Uh, so basically, how does this work? Is if a PC wants to send data to another PC, so uh, so imagine this PC sends a file to this PC. Firstly, it sends it to the router. Then after the router receives it, it sends it to this PC. So every like data, it needs to go to this point, to the distribution point, and that's router. So network is a set of computers that are sharing resources like files, and that's placed on like network nodes. It's like what connects them are network nodes, like router. Oh, and I forgot to explain what's the difference of a switch and a router. Oh, and also what's a router? Router is it's a device to like connect multiple uh, devices so that they can communicate with each other. Like this router, it can make these PCs like communicate to each other in a centralized way. Wait a second. So uh, by the previous example, if this PC wants to send a file to here, we have how does a PC identify another PC in the network? So imagine, for example, we make an addressing system. So an addressing system is basically like, well, an address, like where does something live? Like where do you live? You tell your address. A computer in a computer network, the computers also behave the same way. So, for example, in this example, to illustrate how addressing works, I'm going to just use a simple numbering system. So imagine this PC is called PC1, this is PC2, this is PC3, this is PC4. So from the previous example, PC4 wants to send a file to PC1. Firstly, it sends it to the router. Then the router reads it and PC4. So the file's from PC4 and it wants to go to PC1. The source is from PC4 and the destination is PC1. And it sends it and then PC1 receives it. But we have a problem. What if our network grows not only from 4 PCs, but actually and grows, and then it's not only like in one building we have like a small network, but what if you have like multiple buildings or a city or even a country and it has like multiple networks, and then each network is connected to another network. It's going to be a hassle to like address them. Like for example, like this. And also each switch and router needs to have an address. Actually no, never mind. A switch doesn't need to have an address, but it can. So imagine like PC1 wants to send it to PC14. I mean that's pretty simple, but what if like I said, it goes like a country, like each network in the country like connects to each other, and then each country network connects to another country's network, and then it just grows, and it gets too big. And how that and what's that the problem? Because imagine, so basically there's like over 2 billion computers in the world, like servers, PCs, and laptops, as in like 2014, which was like 2014 was like 7 years ago, I believe. And imagine like the first computer has like an address of 1, and the last computer has like an address of 2 billion. I mean, and also how a router stores like where's the address located at where. They store it in something called a routing table, and if a routing table is going to have like more than 2 billion like addresses, that's going to like take a lot of processing power, because router like determines like the roots of like network packet, like how the data flows from one endpoint to another. I'm going to explain routing in a moment. So this is like not an optimal address system. So to address this addressing system, so but before that, well, routing is essentially like picking a route to reach the destination. So if this is like the source, and this is the destination. Imagine for the previous example, imagine if source A wants to send a image to source C, to destination C, and then when the file gets to router 1 will determine which is the best route. It can go here, or here, or here. It has like 3 options. So it will have to decide which one is the best. It will have like an algorithm to decide which is which. Then imagine if that algorithm decides that router 4 is the best option, and then router 4 does the same. It has like 3 options, but decides that router 7 is the best, equals to 7, then it reaches the destination. So routing is like the act of like determining which path is the best to reach the endpoint, the destination. And well, with a network addressing like this, it's going to take a lot of like processing power for a router to determine which path is best. And so to make a routing table, to store data in a routing table more efficiently, we need a better addressing system. So how do we do that? So we divide the network and make like subnetworks. So we can achieve something called route summarization. So I'm going to talk about subnetworks later. Subnetting networks, subnets, also called subnets. Then uh, so in route summarization, it's basically like it's like summarizing like the addresses, so that the router doesn't need to know all the addresses; it just needs to know the network. So in the current addressing system that from the from this illustration, if we add another number on the front, imagine if it becomes like the group. Like imagine you want to imagine like this belongs like uh, imagine the front number belongs like some group, and then the other number it determines like the identity of that device. Let's just call the first part of the address the network uh, part, and then the second one the host number. So if we put an example into perspective, imagine in this area of the network, it's like in the network one, and then each host, like each PC, has like uh, this his identity is like 1, two, and this is 3. It belongs like one network. Then this belongs to network 6, and this belongs to network 3, and then all of them are like connected to this router. This router can also have like its address, and then also it needs an address, because if a PC wants to send data to somewhere, it needs to know like where to send it. If it doesn't know, well, it's going to send it like everywhere. If not, it's just going to say like here. So to know where, so it needs to know like where this is. It needs to know this address, so it can send like data to it. But then I think we're lacking something. Oh yeah, and I forgot to mention. So the router would read like in here we have like network 1, here we have network 3, and here we have network 6. And if imagine this PC wants to go to here, like I have to send data from to 3.6. So it sends it to the data to the switch first, then the switch like 3.6. I think the router has that. Then it sends it to the router, and the router will read it's like address like network 6 network 6 sorry network 3, and what it doesn't know like each host, but it only like summarizes like network is here, but the host is probably there. So it sends it to the switch, but the switch knows like each host, each endpoint, but it doesn't know like other networks. So a switch is a device to connect n host in the same network. So routers like connect devices from different networks. It connects devices like this PC from network 1, and then connects from the devices from network 3. But a switch can only connect devices, inter-devices, from network 3 to network 3. It can't connect a device, for example, if there's a device connected like from network 3, and then this device from network 1 connected to the switch, it cannot communicate, because a switch is not capable of communicating, establishing connections internet, except a multi-layer switch, which has the capabilities of a router and a switch. Hence, it's called a multi-layer switch. But I think we're lacking something. So what if we expand the network and the host segment of the address? Like imagine like the network like grows like globally again. It's going to like lack number of groups. So if we just add another number on the front, or maybe 2, and then on the end point is going to be the host the host number, like that. So it's like different on each device, and the front part is going to be like the same in the same network on like every device. So the group is like, it can be like, so imagine if there's two network addresses, and this part is like 123.45, 123.45.67. It's going to be different to 1.3.45.68. They're different networks, and to communicate with each other, it is routed to connect them. And also, if if those two IP addresses from two different hosts, like imagine there's like two PCs, one has like a network of this, and then the other one has like this, but this is 68, but this is like the same. They're like different addresses, and they belong to like different networks. Like the host number, it doesn't matter as long as, well, it does matter in a small network, but if it's like the same, almost the same, it's similar, it doesn't matter. So then that's what's called IPv4. So that's like 4 numbers here. So this is a ported. So IPv4 address, it has 4 portets. Then what are the features of IPv4? Oh, and also forget to mention, IPv4 is what we use on the internet. The features of IPv4, as I said before, it has 4 porters, and then it's actually a 32-bit integer value. I'll expand with that later. And then this is another example of an IPv4, and the IPv4 some addressing system. It has a total of 4.3 billion addresses, and back in the days, the engineers who designed IPv4, the network engineers thought that IPv4 is good, like it's going to be enough for like the whole world and stuff. But spoiler alert, it's not. Oh, and also, each IP address is made of 4 numbers, like 4 quartets, and each number has values between 0 to 25. So each value, like this number, or this, or this, or this, can only be in between of 0 to 20 to 255. It cannot have, like, imagine here, it has like 254, it's valid, but if it's like 256, it's not valid. And because it's actually like it's actually a 30-bit value, and like bits, they're like they're set to binary. And how does this like work? Like this is like a 32-bit, and a bit is like it's from the binary numbering system. And like in binary, you have only 2 numbers, and the 2 numbers are only like 0 and 1. And the combination that we use normally is it's called the decimal numbering system. So how do we count binary? Well, I'll teach you in a second. But an IPv4 address consists of like 8 bits per portet. So this portet has like 8 bits. This also has 8 bits. This also has 8 bits. And this too. So 8 times 4 equals 32 bits. But imagine like writing IPv4 in like the binary numbering system. That would be like a hassle. So it's usually converted to dot decimal notation. So it's for ease of readability. And so before this, I'm going to explain you how does binary work. So in this game, it's going to show like some binary numbers, and I'm going to show you how binary works. So once again, it's called the binary. So this binary, this 8-bit number, it has 8 bits, and basically this digit has a value of 1, this has 2, this has 4, 8, 16, 32, and 64. I don't know if you can see that. Yeah, you probably can see that. And you also cannot see that. Oh well, I don't know what to do. Well, basically it has here it has 1, it has a value of 1, this has 2, this is 4, this is 8, this is 16, 32, 64, and 128. And so this times 2 equals 2, this times 2 times 2 equals 4, 4 times 2 equals 8, and so on until 128. So 8 bits, if all of them are like 1 plus 2 plus 4 till plus 128 equals 256. In this 8-bit integer, it's like 0, 0, 0, 0, 0, 1, 0, 0. It has the value of, like, the 1, it means that, oh, it has this value, is 4. If it's 0, just don't count it. It's like 0 times 1 equals 0, 0 times 2 equals 0, and 1 times 4 equals 4. And here 0 times 8, 0, 0, 0, 0, 0. So 4 times 1 equals 4. And but this is not to what's this number. We're going to change these values to match this number. So this is 2, and 2 is located here. So that's right. If it's right, it's going to collapse. So 5. Oh, so it's here we have 4, but we're missing 1, and here's a 1. So 4 plus 1 plus 5. Now here is 16. This number 1 is located like on top of 16, and there's like no more numbers that are like make them like beside 1. No more numbers that makes the value like that adds the value. So this is like only 16, and here it's only 2 and 1, so it's 3. And here there's 12, and we need to match that. So what makes 12? Well, 8 plus 4 is equal to 12, and here's an 8, and here's a 4, so here's 12. So, and this is 255. How many ones do we need? Well, all of them to get 255. Sorry, that was one mistake. If I said 256. 34, we need to match here. 4, it is 4 here, and 32. Here's a 32 here. So we need this only need to be like on, and there's like off. There's like 63, and the trick is in here there's 64. If all of them like on, it means that 64 minus 1, and 84 is like off. So this is 63, and here is 11. 8 plus 2 plus 1 is 11. Then here's 2, so it's 2. And here, oh, this is the match. And here is like 32, and here's like, or not, I suppose not the country. So, done. Okay, so that's some explanation. So, the previous example, there's like, here, 0, 0, 0, 1, 0, 0, 0, 0, 0. And here there's like, it has a value of 1, and here 2, and here is 4, and here 8, and here 16. So there's like 16 only, like, it's like on, so it's like only 16, and there's an off. And in here it's like, if all the values are like 1, it equals to 255. But the value of like 1 here is like not on. So 255 minus 1 equals 254. And here too is only 1. And here, 128 plus 32 plus 8 plus 4 equals 172. That's a brief explanation of how to count binary. But as I was explaining, the previous engineers back in the days, the engineers thought that before was like was sufficient for each device on Earth. It was not. So there's a problem with this. And if we look at this graph, so this graph is about how many IP addresses are there in the world. Oh, and I forgot to explain that the network on the internet. The internet is like short for internetworks, and hence why internet. And then in the left part of the graph has like how many IP addresses how many IP addresses pools how many IP address pools are there is on the public internet, like the big internet, and then in the x-coordinate of graph, it's a timeline. So with each passing year, it declines. So there's so we have run out of IP4 addresses, and each of these is basically like which IP address pool block is located, it's assigned to. Like Arfinic is like in Africa, and AP, if I'm wrong, is Asia Pacific. Iran, I have no idea. Right, I also have no idea. And Lacnic probably will be like that. So it has run out. And here's the timeline of like when was what designed. So in 1980, in the 80s, IPv4 was the standard, and then in the early 90s, the first ISP was commercialized. So an ISP is short for Internet Service Provider, and it's basically provides internet. It gives out IP addresses, so computers, devices can connect to the network and browse the internet. Then the creation of routing and addressing group. So the addresses was grouped and stuff. And then in June in 1992, there's the first exhaustion problem. IP addresses was decreasing, and then the CIDR was proposed. And CIDR, it's a system it's a concept to expand the IP addresses port. So before this date, IP addresses was classified into 3 classes. So there's a class A, class B, and class C. Class A was for like 16 million hosts, and class B was for like a little less than that, and then class C was for like a private network with only 256 hosts, if I'm not wrong. But that was a problem, and with CIDR, which stands for classless interdomain routing, it basically makes the class A, class B, class C deprecated, like it's like thrown away, but it's still like used historically for conventional reasons. And with CIDR, it doesn't matter if it's class A, class B, class C. Oh, and class A, by classes I mean like the network part of the IP address, like the first part, like 192, it's like the values are like classified like from values in between, if I'm not wrong, 0 to 10, it's like classified as A, and then to like there's like something to, if I'm not wrong, 11. I'm sorry, kind of forgot. And then 170 to somewhere, it's classified as C, if I'm not wrong. Can you search it up? IP classes. Then CIDR basically just ignores that, and every like value can become like it can supplement, make like the network have less hosts but more networks, like more network variations. on any value. And then in May 94, NAT was proposed. It stands for Network Address Translation, and it basically so in private networks, like networks not connected to the internet, can use like private IP addresses, and it doesn't matter if they're like the same on another host with on a different network. If they're behind another network, it basically just makes the private IP addresses like can connect to the internet. But it still doesn't like really solve the problem. But by actually providing a solution in December 1969, 1996, IPv6 was proposed. And then in January 2011, again, was which is the organization that gives out IP addresses, use the last free /8 address block. /8 is basically means like imagine a network address, and this means it has like 60 million hosts, and it was exhausted, like the last big like address block, and so on. So if you do a quick Google search, it says that number 25, 25th November 2019, we finally run out of addresses. In the blog, it says, in the article, it says that the last 16/16 block. So if the smaller the number, the more network hosts it has, host numbers it has, the bigger number until /32, it has like smaller hosts. So why is it like from /0 to /32? It's basically from here. This has 32 bits, and then from 8. So /8 is called like a prefix, and the prefix like decides which part of the IP address is going to be the network part of the address. So /8 decides that this part is going to be the network, and all of these numbers are going to be like the host. So if these are if this was different, this value is different, this value is different, and the network like 172, like, and it's with the /8 prefix, and like two hosts. A host has this IP address, another host has this, but these values are like different. But this 172 is like the same, and it has a prefix. Both of them have a prefix of /8. They can communicate. So it takes /8 from here, the binary numbering system, and /16 basically divides it here. So 8 plus 8 is 16. So this part is going to be the network part. So these numbers are going to be the network parts, and these ones are going to be the host parts. And then /24 is here. So 8 times 3 equals 24. So this part is going to be the network, the network segment of that address. So with 3 octets being the network segment, the last octet is going to be the host, and if you calculate, there's going to be 240 and 54 hosts on prefix of a /4 prefix network. So what now? Well, if you've been involved, something called IPv6 proposed, and I'm going to explain that. And introduction, but introducing IPv6. So, what's the difference of IPv4 versus IPv6? But where's actually IPv5? That's an interesting question. So IPv5, it's like the first version of the Internet Protocol was developed to stream voice data and video. So it's to improve like streaming like videos and having like voice chats, voice calls, and it was collectively developed together by Sun Microsystems, Apple, and X. Oh, and Sun Microsystems, I don't know, they were acquired by Oracle, that Oracle has like, if you know them, if you have heard of them, you probably know them from VirtualBox or their database and stuff. And well, Apple, well, that's obvious. Then next, yeah, I don't know. Well, they developed it on an experimental basis, but before it could be brought into public domain, they also came out with another version of Thinking Protocol called IPv6. So basically, why was IPv6 like came out before IPv5, and IPv5 is not used anymore, and this is used on an experimental basis. It's because when IPv5 was like developed, and it's like, oh, this is great actually. It improves like the video and it improves streaming. Basically, IPv5 works the same as IPv4, but it's like better. But then IPv4 was upgraded, and so that's why IPv5 is not used anymore. Oh, and IPv5 also has like 4 I don't know, 4.3 billion addresses too. So yeah, then IPv6 was developed. So now we can use IPv6. So what's IPv6? Here's an example of a ridiculously long IPv6. And yeah, it's super long, and you know what? It has too much host. Like we're probably not going to run out of IPv6 addresses anymore. And this is really difficult to read. You wouldn't want to like read that out loud. So to not make things too complicated, we're going to simplify it. And IPv6 can be simplified if it has a string of zeros. So 0000 is a string of zeros, and can be simplified to change to be nothing. By nothing, I mean like two semicolons. So two semicolons can signify like, oh, in here there's like an empty string of zeros, and the computer can calculate like, oh, here we have like 4 times 5. So here we have like 25 digits, and and um, and in here and in IPv6 address, it has like 32 digits. Oh, and I forgot to mention. So IPv4 works on binary file numbering system, but IPv6 works on the hexadecimal numbering system, and that's another numbering system. And IPv6 has it has like 16 numbers from 0 to 9, and then F, and then A, B, C, D, E, F. So it uses letters to represent values. Like A represents one value. Like A equals like 10, B equals 11, C equals 11. Wait, no. C equals 12, D equals 13, E equals 14, then F equals 15. Like if you add them numerically. So this is like only one digit can have like a value of 10 until 16 until 15. So that's why. So in here, like the computer can like calculate, oh, in here we're missing a string of zeros, and how many strings of zeros can calculate this and subtract it here. But you can also like simplify this by turning it into just a zero. But why not do it like this, like semicolon and semicolon? Well, if you do it like that, the computer will not know where to fill the zeros. If it fills the zero here, and then it fills the rest of here, but is it like the same address like this one? It's probably going to be different. It's going to have a difficult time to design. And so, and also another way to simplify an IPv6 address, if the front of this part, like a part, like a four strings of an hexadecimal, it can like be erased, or another. If it begins with 0, it can be erased. The zeros can be erased. So here, this. And here we still have the semicolon, so it's more zeros. Then well, before we go further, are there any questions? I'm going to wait for 5 minutes, and I'll be anticipating if there's any questions. I hope I can answer them have guys. So there's a I'm going to 3 minute break.
Okay. So in this session, you can ask questions to our presenter about IPv6 and another lesson that before. We're gonna wait until about 2 minutes. If there no question, I'm gonna continue the lesson.
Okay.
Okay. We will continue the lesson. There's no question for time, presenter.
So if there are no questions, I'm going to continue the webinar. So in here we have an example of an hexadecimal. So an hexadecimal number can be also called hex. It works as like almost the same as binary, and so this value has like 15. It's 15, right? And then here's like 2, and if the front number has a so it begins with just has a value of like 1, and then times with like this value f. So 1 times f equals like 15. But in here, it has a value of 16, and then 16 times 2 equals 32. 32 plus 15 equals 37. But that's like kind of complicated, and so if you want to like you can also convert to binary by just like splitting them up, and then you split them up to like 2 nibbles, and a nibble is just like half of an 8 bit of 1 byte. And 1 byte is like 8 bits, so a nibble is a half a byte. So an f, so it's like all the values are 1. So 1 plus 2 plus 4 plus 8 equals 15. So it's 15 equals like f, and in here, well, only 2 here, so equals like 2. So then the binary notation, the binary representation of this is this 0 0 1 0 0 0 0 1 0 1 1 1 1, and like to fill in the gap, well, to make it like yeah, it's from here, just to make it like a byte. So what's the difference of IPv6 and IPv4? Well, in IPv6, it's like so um, it's 128 bits, and then an IPv4 is 32 bits or 4 bytes, and here it's it's 16 bytes basically. So on IPv6, uh, its size is like 16 bytes, and IPv4 it's 4 bytes. It's like 4 times of it. So uh, for IPv4, it has like a total range of 4.3 billion possible addresses, but an IPv6 has like 340 undecillion possible addresses. And if you want to see that number, well, let me show it to you. IPv6 auto reach. Yep, it's not showing up here. So, here it is. So, it, how many total addresses? Well, it's basically just like 2 over 128. And yeah, this is the total possible addresses, usable addresses of IPv6. Let me zoom in closer if I can. Here. Yeah, 340 undecillion undecillion something. Yeah, that's IPv6 compared to just 4.2 billion. So it has like in the scientific notation it's like 3.4 times 10 to the power of 38. Some of the blocks of the space and some specific addresses are reserved for special uses. So, how in IPv4 you have like the prefix to divide which part of the address is the network part and which part is the host part. In IPv6 you also have something similar, which is called the prefix. The first part is like the prefix, and the second part is like the identifier. It's basically just the same. Oh, and also, so a packet like a data, it needs to be like formatted so it can be like sent to the internet, and other computers can read it. It would be like in a special format, and it's basically this format. And so in a IPv4 header, like the like a part of that data packet, and it has more fields, but in the IPv6 header it has less fields. Here you have like in IPv4. Oh, and also in IPv6 it has built-in security. It's called IPsec, like IP security, and it's like basically it's encryption. But in IPv4, well, no, you need to like edit or something. You need to add. It has this thing called authentication, and it only has like two types of authentication, like plain text and MD5. But in IPv6, you have like three types of IPsec, types of encryption, IS, and third ones. So, and also to identify which like associate the prefix part and the host identifier part is equivalent to like the network and the host part. The maximum slash like prefix is like /128, and those are usually used for loopbacks. So beside that, I'm going to show you a poster of IPv6. Wait, sorry for the inconveniences. So sorry for the delay. So in here, here's a very nice poster of IPv6. So that's a smaller header compared to IPv4, and then there's like three iris types: unicast, multicast, and anycast. So in IPv4, there's no anycast, but there's broadcast. But in IPv6, broadcast is like it's deprecated and it's replaced by multicast. So what are these iris types? Well, it's basically if a PC sends like uh, uh, a packet to like switch can like, and then another one is a UDP, also called Turtle. Then another one is like ISATAP, which stands for Intersite Automatic Tunneling Addressing Protocol. And then um, another method is through translation. Just translate the IP address fields. Oh, and well, that's basically it. So now we're going to, if you have any questions, feel free to ask in the comment section. And I'm going to wait for 5 seconds. So then we can continue to the rest section of this webinar. So, so well, routing. So what's routing? Just determining like the path, like the data basically. And so this are, imagine if there's like two paths, like which one is like the best path and stuff. I'll explain like what's routing before. Now we're going to talk about IPv6 routing. We're going to do uh, some basic configuring, some basic configuration. Okay, so in here we're in Cisco Packet Tracer, and it also has to communicate to simulate networks. And here are two routers. I'm going to connect them, and I'm going to turn on their interfaces. So first, no, enable, I'm turning to executive accept mode, then entering to interface gigabyte 000, then turn it on, and then also the other router doing the same thing with it from user mode to privilege mode, then going to global configuration mode to change the settings, configure it. So when you do the same, then now shutdown, turn it on. Now the interface is on, and now there's like I want to show you how to do routing with IPv6 two ways. The first one is to static routing, and the second one is to dynamic routing. Dynamic routing. So there's like a lot of ways with dynamic routing, and static routing is something like this. Well, it's static. You configure manually, and it's only one way. So first thing we're in the interface that's heading to the router, and we're gonna add IPv6 And usually, if you add an IP address to an interface, you just tap IP and add, which is short for address. So you can just type it as add IP add, for example, this IP address. But with IPv6, you just add a v above it, and yeah, that's like every IP command just changes to IPv6 from IPv4 to IPv6. So IP add, and then in this interface, I'm going to just name it like both 7.7.1 126, just 126. So I finally, like, finally, this is funny. Like in IPv6 in Cisco, you can put prefixes because if you write it in a NatMas in a NatMas, it's going to be like really really long. But not IPv4 one. So yeah, the NIP address. Oh, and also another a loopback address. And a loopback is basically like a virtual interface that can't be shut down. Well, like errors can happen with physical addresses and they can be shut down like by accident, but not virtual interfaces. So a virtual interface can be used, for example, like, to put it in simple words, an identity of router. So during the interface loopback, put that in our IPv6 address, which is one. So keep things simple. Then on router 2, I'm going to do the same thing, but the address is different. Then look back. Send it to another PC, but in multicast, if a PC sends a packet to a switch, the switch can send it to multiple devices, and so on. And in Anycast, sender is configured in multiple locations. So an example of this, like mobile phones can have like the same IPv6 address on one location, and then if that phone moves to another network, it's going to have like the same address. And then there's multicast scope. Then there's like special use ranges, like the prefix ones, and also colon means like 00000 and 0000 means like it's like the scope of like everything. Like 0 means like sometimes it's like, but it's only 0, like in like maybe like 100, like in IPv4 192 point 168.10.0. That's basically like the 0 is like represents like the network basically. Then here's like unspecified. This is a look back. This is deprecated. And then Gerdo, it's an interesting thing where it's used for, if I'm not wrong, tunnels or dual sex, if I'm not wrong. Then 624, it's another tunnel. Then unique local, it's unique to the locally unique. It's like for LAN, local area network. And then a link local unicast, it's also it's not advertised to other networks, so other networks don't know this address. It's only known on like the interfaces that are connected to each other. And then this is deprecated, and then multicast. So as I said before, remove these blading zeros from all 2 byte sets, then can replace like semicolon or just 0. And then there's 3 types of address formats. So global unicast, you can say which the global prefix, subnet, and interface ID. Interface ID, as I mentioned, is like the identifier, and the first part is like the prefix, like which type of address it is. And then, so basically IPv6 there's like so IPv6 there's like it can be configured in like two ways, either static or dynamic, and IPv6 can be configured in four ways, like two ways are static and two other ways are dynamic. So the two static ones. The first one is to um, configure it manually, like entering like each hexadecimal character like manually, and the other way is to um, use this thing called EUI64 formation, which basically takes the MAC address of that interface. Oh, and an interface means like the port where you plug a cable. So it just takes it, splits in half, and then inserts an FF, FE character string, and then in first, the first, and in this part, and in this first byte, it's going to change the 7-bit to 1. So it's basically just like it first converts this hexadecimal character into a binary character, and then at binary you're going to change that, flip the 7-bit, and then you convert it to hexadecimal again, so it changes here. So that's IUI44, IUI64. So those are two ways of configuring IPv6 manually. So the two other ways are dynamically, which is like automatically configured, and they're provided by usually routers or these DHCP servers. And DHCP servers are usually services in routers. And the two ways of dynamically setting up an IPv6 is through DHCP v6, or to something called status auto configuration. It can be shortened to SLAAC, SLAAC. So I forgot to mention, but IPv4 and IPv6 are not compatible. So protocols cannot of each other cannot work, and vice versa. So protocols are just basically, by definition, they're like a set of rules. So for a computer can communicate to a computer, it needs to like communicate in the same language, and protocol just like sets up that format, that language, so they can communicate with each other. Like, you know how can't Chinese communicate with an Arab because they have different languages, but they still have this thing called gestures, so they communicate that way usually, or anyone who can't like communicate with another person. And then there's extension headers from the header, the format, and then there's transition mechanisms. Like, because the internet is like told like for IPv4, it's going to take time to migrate to IPv6, and there's like ways to use IPv6 to migrate IPv6. First is like dual stack, secondly tunneling, and thirdly translation. So dual stack just like uses IPv4 and IPv6 like simultaneously, like both of at the same time. So imagine like your laptop gets an address from a router, and that address is an IPv4, and it gets another address which is an IPv6. So sorry to revise a bit. So the interface of your laptop gets two IP addresses. One is an IPv4 and another one is an IPv6. That's basically it. And then another method is like tunneling, which IPv6 traffic is like basically encapsulated, like formatted into IPv4, and then through like different lot of types, through different methods. One is like IPv16 IP, IPv8 IP. And so here's so in this router, sorry, for the technical the technical sense. So here in this interface, we're going to turn it on, and then we're going to add an IP address, an IPv6 address, and also the interface, the loopback interface too, in here too. So as you can see, on the link gigabit Ethernet 0/0 is up, and it has an IPv6 address. So now we've configured IPv6 interfaces, and to so this router, so that this router can reach this router's interface address, it's like configure an IP static root. So to do that, just exit configure if mode, then IP6 route, then the destination, which is the loopback of routers 1 router 0 IP address, and then through what interface to which gateway, sorry. So if you confused about something, just press question mark, and usually you can just put any interface or the next one, which is the gateway. Then do the same thing to here too. Then IP6. Actually, you can just do it instantly. Then but to keep the addressing simple, the network like 12, like 1, 2, colon 1, like 1, 2 is like, so row 1, row 2 is going to like close like row 1. So let's start showing. Oh, here it is. So row 1, start showing here. And router 2. Here it is. Row 1 and row 2. And after that, we are going to test its connection by ping. With ping, you can test the connection. Then exit on global skirmish mode to ping, and ping the loopback, and it works. Success. That's how you configure static group. And then I'm going to show the routing table. Oh, it's changed every IP to comment of IPv6. And here you go. It's directly connected, and it also has a static route to the other loopback interface of the other router. So that's static routing. I'm going to move on to dynamic routing, and the first candidate is RIP-NG. Well, RIP is a pre-opt routing protocol, and NG stands for Network Next Generation. And RIP is very simple basically. And to enable dynamic routing, you need to config to enable unicast routing. And now you can do routing. It's done on both routers. Yeah, there. So both of them have their unicast routing enabled. Then we already have like IP addresses and stuff. Their addresses are already set up. We're going to delete the static root of each device. So no IPv6 true to the loopback. Oops. IPv6 true. Oh. just going to print it first. Print the following table. Then I'm going to delete the root. Just 8. Oh yeah, slash 8. Here's 58 and file and our table. So now that root is elemented, so deleted, we're going to delete this one too. So no, like the same command, no ib6 root 1 slash 8, then 12. So their set roots are now deleted. We're going to try and so we're going to try and configure another router. Is that another router? And we're going to configure the turn on light device. In here we're going to change it to our tree or tree. Interface UI1 shutdown. Then we're going to add the IP address, IP6 address of 23 and colon 2 and slash 126. Wait, sorry. Add. Okay. Then let's see it. In here too. No. Gigabyte 0. No shutdown. It's on. Then IP6 add button tree, colon tree for like trees and for like broad tree for like education purposes. 8, then true, and that's it. Now, yeah, where it is. Oh, and then also we'll get the loop back, which is create other mystery. So IP6 can't be like friendly with this. It gets a little time to get used to it for those who work with SV4 before. Oh, and also enabling unicast routings for that, sorry. That's it. Put that. So to enable RIP NG, you need to activate it on each interface and on each RIP process ID. Like in Ascot, there's a thing called process ID, and here you can like name the process ID too. Like you like imagine the interface interface that's having to the router too, and then I enable IP6 RIP, and then in here we can have a word to identify the RIP process. I'm just going to put this TED Talk weekend WWT, then enable, and then their interface to also enable it. So to enable, by enabling the RIP in each interface, it's going to advertise that network, so other routers can know that network. So they learn about that network and oh, that's located there. Then if someone request has a destination there, just send it there. And RIP, so that's it for R1, and do the same thing for R2, but you can do little shortcut by having face range, gigabyte 0 to 1, then IPv6 RIP enable. That's it. Oh, and also the loopback for that. Interface loopback enable. That's it. And here too. Router here too. And can you do this actually? I don't think you can do this. I can't use like a range command. IPv6, rip, the name of it, the name of the process, and then enable. And also the webpack interface. Okay, so it's enabled. Everything is enabled. So each router's routing table. So to show in global config mode, do for commands in privilege exec mode, privilege exec mode. Do show IPv6 route, and here route, then rip. Sorry. Yep, I have no idea why it doesn't work here. So basically, here we have rip. We learned rip from gigabit 00, and it's basically this one. But we have not learned rip from here. That's weird. Let's do some troubleshooting. Show IP6 routing root, then wait, can I do that? Oh no, you can only do IP6. And nope, we have not advertised anything. What is that? I have no idea. Let me show the whole config. Check it. Okay. Enable test addresses. Wait, unicast routing is enabled. I have no idea why that. What about other one? Let me show IP routing. And it has turned rip. Then let's show the whole configuration. So the server class routing, then each address is like enable. There's router rip here. Why doesn't it work? It's supposed to work. Oh well, it only works on one interface. So that's a bummer. I think I misconfigured something. Oh. Okay. Oh, here it is. The prefix is wrong here. The prefix of the IPv6 address of the gigabit 0/0 interface wrong. Haha, found it. I made a typo there. A single typo can make the whole network collapse. Same with coding. The single typo, a single space can make the whole code, not one. So that's this IT. Oops. I'll just remove state. Then I put this. Then now it's supposed to work. Let's see if it works. It doesn't work. Great. These are like troubles for network engineering. Here, 36. IPv6 already. Yep, nothing works. So yeah, so that's RIP. Sorry for sorry, can't do anything about this. It only takes like the first shower, and not the second, the third one. What's wrong with it? It's supposed to work though. They have the same network and graphics. But yeah, it just doesn't work. Wait. I have no idea why. Let me see, show calculation. Good. Okay, never mind. Okay, I just leave it like that. So this part of the network works, and this doesn't. And just let me do ping. It works, but not on the tree. Yep, doesn't work. Fine. Okay, so this is RIP. And here, after this, I'm going to show you how to configure SPF. So firstly, we're going to delete each root on every on every row. We're going to delete every RIP protocol, every RIP configuration. So router RIP, and I'm just going to copy paste that. Copy, paste, then paste. Basically just deletes all of it. Wait. Oh yeah, I forgot. And paste. So now it doesn't have RIP in it, and this row doesn't have RIP or any other rows. It only has the loopbacks and the connected interfaces. So to configure SPF, we need to make the process ID. Firstly, make a 6 router, like IP router, OSPF, same thing. Then the process ID. Then process ID. First, you need to configure the router ID manually, and this is Navi before format. So 1.1.1.1. Then you accept. Then enable SPF on each interface. Interface 0, IPv6, SPF, process ID, then the area, which area will to be in. Then you go back, IPv6, SPF, then area 0. Then that's for route 1, then route 2. Oh yeah, we're gonna make the process ID first. Then ready. Router SPF. Then RIP 2222. And then we're gonna go to each interface. Then enable SPF for now. Area 0, then go back to, and on route 3 too. So IPv6, router OSPF, and already 3 then interface 0, IPv6, OSPF, and area and then also double back 2. That's basically it. Oh, look. Sorry, rolling. That's neighbor. I have no idea why this doesn't want to load. Just doesn't want to at all. It's on the same window. Yep, it doesn't want to. So, but we can also we can only repeat one. And that's it. So in this webinar, I'm going to show you this Paragon SPF, and uh, I'll be closing this webinar. Sorry if I've many mistakes, and I totally did have a lot of mistakes. And sorry for trying before, and thank you for listening and watching. And I'm going to transfer this to the host.
Okay, thank you for the viewers of the IGN Talk series who have watched this event from start to finish. For this webinar will take place every Saturday and Sunday morning every week to share knowledge that has been found in this school. This webinar is held for free by IDN, and I'm Anif Fatih as the host of IDN Talk series, saying goodbye. Hopefully, this IP4, IPv4, and IPv6 and routing IPv6 webinar can add the add this insight for all of us. And that's all for us. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.